Hey everybody, Mr. Lee here. In this video we're going to go over a E-fields problem. Yeah, let's begin. So a couple of things about this problem. This is a standard problem where you have two charges and you need to figure out the net field at a specific point. Okay, so for this one we have two positive charges, we'll just call them positive Q, and they are a distance of A apart, as we can see right here. Alright, so question A asks the E field at point P in the diagram below. What is the E field at point P? So let's break this apart. Remember, the very first thing that you should always do is sketch out the scenario. And so I have a sketch here, and please pause the video and sketch it yourself. Now, the next thing I want to do is I want to break down this problem with a E field model. So there's a couple of ways of doing this, and I'll show you both ways here. What I want to do is I want to draw the E field model with the two charges. So I have Q and Q, and if I were to just do a quick, oops, that's exactly the opposite of what happens. If I were to draw a quick model here, okay, we will know that because they are like charges, okay, they repel. So we have a model that looks something like this. Once again, a very quick sketch of what's going on. All right. So point P, which would be like somewhere here, we know that the E field from the left Q, I'll do that in this color here, will be pointing radially outwards this way, and the E field from the right Q, I'll do it radially outward this way. Okay, so those two fields will add up according to the vector addition, so that we have a net field. I'll make this go a little bit thicker so we can see that, of just straight up vertically like so, and we can see that the model also looks like that. All right, another way to approach this problem is by just going straight to point P. So at point P, right, if I have Q and Q here, I know that because these are both positive, okay, this is from the left hand Q, this is from the right hand Q, so the net Q will look just like that. Alright, so this is the net E field right there. Alright, so both models work, both models give you the same result. Alright, so now that we have that out of the way, let's look at how we can approach this through our formulas. So let's go back to this image here. We have two Q's. I'm going to call the Q on the left Q1. I'm going to call the Q on the right Q2. But just so you know, they have the same magnitude. So in order to find the net E field at point P, we have to find the overall E field that Q1 produces at point P. Okay. So if I were to have Q1 here, and I'm looking at point P there, okay, I know that my E field will point radially up and to the right, and this separation distance is A. And so our formula is E is equal to KQ over R squared. So I could just rewrite this as E1 is KQ over A squared. Okay, I'm gonna go below. The same idea can be applied for Q2, so if that is point P and I have Q2 here, okay, radially outwards, this E field vector will point up and to the left like so, right? And the formula is the same. I'm gonna just take a shortcut for time's sake. We get E2 is equal to KQ, I forgot to label the radial distance as A, all divided by A squared. Okay, so these are the two formulas that we can use for this scenario, and this is where drawing the models help. We know, that according to both of these models here, only the vertical E field component is left behind, and that is because the horizontal components, they actually cancel out according to vector notation. So what this tells us is that we only have to really care about the vertical components of that E field. So if I were to take a look at my two models here, if that is point P, we want not the horizontal component, which I'll draw it in anyway, so this would be E1x, but rather we only want the vertical component right there. We'll call that E1y. Okay. Same with this one down here. This vector is pointing up and to the left, so I'll call this E2x, and we'll also have E2y going vertically. All right. So we only care about the y components in both situations. And so our y components, if you remember, we always break down vectors with the components using sines and cosines. So it helps us if we take a look at the original drawing here. We know if this is an equilateral triangle, this is 60 degrees. This too is 60 degrees. And this up here, of course, is 60 degrees. So if I were to take a look at what Q1 is doing, Q1 is pointing in this direction. Okay. If this angle here is 60 degrees, then if we were to take a look at the vertical component, okay, along this axis here, right? So if this is E1y, we can see that this angle, okay, according to the laws of geometry, is also 60 degrees. All right. And so what that tells us with down here is that this E1y, we can just rewrite the formula of E1y is equal to E1, which is the original vector, but we only want the vertical component, and the vertical component of that will be, let's go back to our original image. If this is 60-degree angle here, the y component is opposite of that angle. So opposite always means sine. So E1y, E1 is sine of theta. In this case, our theta is 60. Okay, so we could write this as not E1, but rather KQ over A squared sine of theta. Okay, and the same is true for E2. So we can write E2y as E2 sine theta, or KQ, so Q2 in this regards, over A squared sine of theta, where theta is in fact 60 degrees. So the reason why Q2 also has 60 degrees, let's break this down even more. If we take a look over here, we know that if we're doing some geometry here, this portion, okay, and this portion, okay, that creates a straight line. We know that this is 60 degrees, so that must mean that this angle here is 120 degrees, because 60 plus 120 gives us 180. So that leaves us with this mysterious angle right there. Okay, and what we can do is we can use the parallel line theorem, where if we have two parallel lines, okay, and the two parallel lines that I'm referencing is up here. So this is parallel line 1, and this is parallel line 2. Right? If we have two parallel lines and we bisect them like this, the angle here and the angle here are going to always be equal. And so for us, this angle here is 60 degrees, so the angle there also must be 60 degrees. And the same is true for the lower right-hand angle, right? So if we have this bisector here, and we know that this is 60 degrees, okay? On the other side, this also has to be 60 degrees. Okay, so we have E1y and E2y. So to find the net E field, we can do E1y plus E2y, which just becomes KQ1 over A squared sine theta, plus KQ2 over A squared sine theta. And at the very beginning of the problem, we said that Q1 is equal to Q2. Therefore, this just simply becomes 2KQ over A squared sine theta as our net E field. All right, so now the question is, where can we place a, if we take a look at question B, B says, determine where a negative charge, negative Q, can be placed in order for point P to have a E field of 0 Newton coulombs. All right, so let's break this down. I'm going to use this model here because it's a little bit cleaner. Now, we know that right now the net field is pointing straight up. So in order for the net field at point P right here to equal 0, we need to cancel out that vertical E field. And the only way to do that is to have a E field pointing downwards. So let's do a quick review of our concepts. For a negative charge, all fields go in towards the negative charge. Okay? So we want a field line that's going downwards to cancel out that vertical field up there. So if we have a negative charge, I'm just randomly guessing where it would be, a negative charge somewhere here. Okay, and if I were to draw the field vectors, let's do this in a different color. Okay, if I have a negative field vector going down this way, okay, we have all these field vectors going in, like so. But if we're looking at point P, from this negative charge, we have a field vector pointing down. And we need that field vector to equal to the net field from the two charges that we figured out in part A. So if we want to solve for part B, where it wants to know exactly where we have to put charge 2, we can set up the problem like this. Okay? We know that, let's just call it the net field, we know has to equal 0 Newton coulombs. And we know that the net field has to come from two sources. So we have E1 plus E2 plus this new E field. I'm just going to call it E3. Okay. We already know what E1 and E2 equal to, and we saw that from before, which is 2kq over a squared sine theta. Okay, and sine theta for us was 60. Excuse me, theta was 60, plus this unknown E3. But this problem is looking for where we need to place E3. Okay, we need to know where we have to place, Q3, and this all adds up to 0. All right, so if you take a look here, at this point, it's just a algebra problem. Okay, we're solving for something that's within E3, so I'm going to isolate E3 all by itself. We know that E3 has to equal to 2kq over a squared sine theta, and of course this E3 is negative, and that negative simply means it's going the opposite direction of 2kq over a squared sine theta. We also know that the formula for E field is negative kq over r squared is equal to 2kq over a squared sine theta. Okay, and once again that theta is 60. So what we're solving for here is r. And at this point, all we have to do is rearrange the formula so that we get negative kq divided by 2kq sine theta. And in the numerator, we have a squared is equal to r squared. And at this point, we can simplify this formula a little bit. I'm going to cancel out a couple of things. We know that the 2k's cancel out. We know that the q's themselves cancel out there. So that leaves us with r squared is equal to negative a squared. And remember that negative simply means direction, all divided by 2 sine theta. All right, so if I need to know the exact location, I'm going to take the square root of both sides and see what I do here. That negative simply means the direction, okay? And so if we're taking a look at this in terms of the magnitude, I can actually take that negative out. Just ignore it completely, because the negative is simply telling us that the E field must point downwards. All right, so r is equal to a squared 2 sine theta and the square root of all that. And if we were to simplify this even more, we will get a square root of 1/2 over 1 over sine theta, and that's an a up there. Okay. So wherever that location might be in terms of coordinates, that would be where we can place the negative charge, so that it will cancel out the E field from the other two charges. Alright, so that is just one problem that we just did. I'm going to actually write a little written statement about this problem. This is a practice that I want you to get used to because it does help out with the FRQs. Okay, so my written statement can be as simple as something like this. Alright, the two positive charges will create a E field pointing vertically upwards. in order to create a E field of 0 Newton coulombs at point P, the negative charge needs to be directly underneath of point P in order for the E field to cancel out to be 0. This is due to the downward E field from the negative charge at point P. Okay, and we can also make a little statement there saying the radial distance from point P was found to be, I'm going to write it down, R is equal to A 1 over 2 sine of theta, okay, or R is equal to A square root 1/2 sine of 60, or sine of 60 is in the denominator. Okay, and that would be my written statement. If this were a FRQ, I'm pretty sure I would have gotten max points. All right, I'll see you next time. Bye-bye.